Unlike with longitude, changes in latitude have obvious effects. After all, travel in one direction and the days become warmer and longer. Go the other way, they're shorter and colder. Scattered across the United States for Thanksgiving break, we observe length of day. Upon return to Harvard, we use this information to calculate our respective latitudes. Bowditch's comprehensive work, The American Practical Navigator, includes notes on using length of day to find latitude and vice versa. Bowditch's method utilizes tables to find this information, rather than calculations. After all, this work was written in the 1800s. The underlying principle, though, is the same. There's an obvious correlation between length of day and latitude for any given time of year. Omega naught, the hour angle, is a way to represent the amount of time elapsed either from sunrise to local noon, or from local noon to sunset. We convert it to an angle to make it easier to work with, by taking the time in hours and multiplying by 15 degrees. Hour angle depends on latitude and solar declination. Imagine a point at a high northern latitude during, say, January. Because the Earth is tilted away from the sun for the northern hemisphere, this point will spend more of its day on the shadowed side of the Earth and less on the lit side. This means it will have a smaller hour angle. Solar declination depends only on the time of year at which a measurement is taken. Essentially, it measures how far away from the sun the Earth is tilted. It can be defined as the difference between 90 degrees and the angle of elevation to the sun at local noon from any given point on the equator. Finally, the quantity that we are trying to calculate given these other two measurements is latitude. The latitude for any point on the Earth's surface is defined as the angle between a line drawn perpendicularly through that point and the plane of the Earth's